Let's try to unpack the meaning of the generator in terms of the rates of the continuous time Markov chain. So we had this definition of a continuous time Markov chain in terms of rates at which it transitions out of any particular state, and in terms of the embedded chain that takes it to the next state. So let's try to relate the generator to that definition. We're going to start off, however, with the definition of the generator that we do have, which is as the derivative of its transition probabilities at time 0. So this is where we're going to start, and we're going to follow up with two cases. One case is x is equal to y. This is a special case because here the probability of transitioning or being in state x, given that you started in x in 0 time, is equal to 1. So given no time, you've clearly stayed in the same state with probability 1. And in that case, we can take this derivative here and approximate it with this finite difference here. So this would be exact if h is being taken down to 0, but here I'm just making an approximation for now. The only quantity that we need to get a handle on is this one right here, pxx of h. And here it is written out. This is the probability of being in state x, given that we've started in state x, being there at time h, that is. And we're going to make a little approximation, and let me explain how this would work. So one way that this could happen is if our waiting time in that particular state was longer than h. Right? If we want to be in state x after h units of time, then we would have had to wait in that state longer than h time units. And I'll explain why there's an approximation sign here. But for now, this is a pretty good description of what could have happened. We could have waited for longer than h, which means that tau, which is the exponential waiting time in state x, is greater than h. And this is just the survival time of an exponential given by e to the minus rxh. Rx is the rate of that particular state. So let's talk about the approximations that were made in all this. The first one had to do with the approximation of the derivative. So the derivative actually needs h to go down to 0 to be exact. But here we've made a little approximation for the fact that h is just small, not going to 0. This approximation is of order h squared. You can try to prove that from a Taylor expansion and other ways. So the next approximation was the one right here, this one, and that's because what I wrote there is not the only way that the event of staying in state x in time little h could have happened. We could have had a transition to some state y, some intermediate state, and then switch back to x before h units of time. The reason that I'm ignoring all this, and the reason I'm putting an approximation sign here, is that these state changes, in a little interval of time, they're much less likely. In fact, if you try to compute those probabilities, you'll get something of order h squared. So that probability is sort of minute, very very minor, very small relative to the order that we're working with. Right? We're working in units of order h, so we're going to ignore terms of order h squared, which is why I'm ignoring these kind of alternative ways of staying in state x in h units of time. And then our third approximation is going to be a Taylor's approximation for the exponential. Again, you see that it's making an error of order h squared. That's the next kind of missing term in the approximation, would be order h squared. But e to the minus rxh is well approximated by 1 minus rxh. So now let's put everything together. Like I mentioned, all three of order h squared, and we're going to ignore them. And if you do them rigorously, you kind of just keep them to the side there, so that you can eventually take h to 0. When you do take h to 0, you'll get this result here. So rxx is equal to minus rx. How does this happen? Well, it's kind of like this. You take this probability, replace it by its approximation, which is this one right here. Apply the Taylor expansion to it, which gives you the 1. This 1 here cancels with the 1 in the numerator up there. And the division by h takes care of the h next to the rate, leaving us with a minus Rx. So the generator of, the generator entry XX is the negative of the rate corresponding to that state. Okay, so easy enough. What's next? Next is the other case, which is x not equal to y, in which case we have a simpler formula. The probability in 0 units of time that we've actually changed state is 0. We had no time to make a move, so that's 0, and therefore an order 1 approximation for the derivative is right here. So it's just pxyh divided by h, and we can look at this probability once again as we did in the other case. This is the probability of moving to state y in h units of time, given that we started in state x. And you can kind of see sort of what has to happen. You know, the most obvious or most likely way that this could have happened is that, first of all, the waiting time has to be smaller than h. Otherwise, we wouldn't have switched states at all. So this definitely had to happen. And the second thing that had to happen is that the embedded chain, which we usually call Z, had to transition into state Y. And of course, this happens independent of the waiting time. That's just by the construction of the continuous time Markov chain. And now we can make the following approximation. I'll talk a little bit about why this is an approximation in a second, but let's kind of digest these two terms. The embedded chain is independent of the waiting time, so I'm just going to multiply the two probabilities that I need. The first one corresponds to the fact that we actually switched a state in the time allotted, right? We're given h time units. This probability is saying we've actually changed the state, meaning the waiting time is less than h. The second probability is that the embedded chain went from x into y, and now if you write out what that is, that's just the CDF of the exponential with rate Rx. So this first term, 1 minus e to the minus Rxh, corresponds to the probability that tau x is less than h. And the second term is the embedded chain probability, the one-step transition from x to y. So why the approximation? Again, I'm sort of dismissing other potential ways of getting to y. Maybe it went through some state z. Maybe it went through several states before getting to y. The point of the matter is that when h is small, then the probability of these kind of alternative paths to y is of order h squared, and therefore negligible. And you can kind of keep them, you can make this all rigorous by keeping those in there. But the final result will be what we're about to arrive at. The third approximation will again be order h squared. It's a Taylor expansion to the exponential here, and that's going to be just Rx times h. And now you can kind of plug everything in. We have here this whole term here, this probability, the numerator of the original formula for the generator is going to be Rxh. We divide it by h, and we get Rx times bxy. Once again, if you had kept the order h squared terms there at the end and taken the limit down to 0, you would have arrived at this exact expression. So what's the final kind of tally? We've started with this definition for the generator. So again, this generator is defining, right? It can be used to completely describe any homogeneous continuous time Markov chain X. And what we're now seeing is that there's a much simpler definition in terms of the embedded chain and the rates for each state, and it's this one right here. So the final thing here is that the generator, once again, something that describes a homogeneous continuous time Markov chain, can be written down in a very succinct form. Its diagonal entries, if we think of it as a matrix, will be the negatives of the rates at each state, and the off-diagonal entries will be determined by each rate multiplying the corresponding one-step transition probability for the embedded chain. So this is a very simple and much more, as we'll see, intuitive definition for the generator that's going to, for all intents and purposes, maybe replace this one. I mean, both are, there, but and both are equivalent, mathematically equivalent. But the second one, this one is much more appealing. Let's talk about why. So the interpretation for RxY, the generator entry XY, it's sort of a way of representing a rate of transition from the state X to a state Y. And you can kind of think of it like this. So Rx is the rate of leaving the state X. That's what it is, because the waiting time is exponential. So if Rx is high, you leave quickly. So it's Rx is literally representing the rate of departing from state X. And BXY is just now accounting for the fact that the final state, it's kind of like redirecting this movement out of X into the final state, which is Y. BXYs are all smaller, right? And so you're kind of taking the total rate of leaving state X, and you're multiplying it by some fraction, which is sort of accounting for the likelihood of ending up in state Y. And then RxX doesn't really have an interpretation as a transition, because you're not actually transitioning, hence the entry minus Rx. So it's maybe some of the kind of this interpretation breaks down a little bit at the RxX entry, but in a way RxXX should not have an interpretation of a transition. You're not really transitioning from X to X. You're always waiting in a particular state. So what we can do now is come up with this conservation of rate law for the generator. So what is conservation of rate? We're going to sum up the rates, kind of much like we did sum up one-step transition probabilities to get 1. We're going to sum up these rates over all states Y. The first one that we're going to take out of the sum is the one corresponding for something that's not really a transition. So it's the one for Y equals X, and it's equal to minus Rx. So that's the first term we take out. And the remainder of the sum is going to be over all Y not equal to X, the thing that we just took out. And plugging in the definition of Rxy gives us Rx times this sum. And what you'll notice is that kind of either way you cut it, in the end you'll get that this whole thing is 0. So this sum will either be 1 if the transition out of rate X is greater than 0, or it will be 0 whenever Rx is 0. This has to do with the fact that the embedded chain can only have a self-transition when the rate for that particular state is 0. So we've looked at this calculation a few times, or this definition of the embedded chain a few times. Either way, whatever the case may be, you get the following conservation law. The sum over the rates Y starting at X is always 0. So this is a conservation law for the rates. Alternatively, you could actually define the rate of leaving a state, the state X, as the sum of leaving the state X for some other state Y, which is very intuitive, right? If you sum up over all the rates of going to all states Y, what do you get? You get the total transition rate out of X. So that's another way to interpret this conservation law.